So here is the today's topic, which in terms of the content is actually not that many in terms of the slides, but in terms of the importance, I would say this is one of the most important topics that has to be has to being discussed in deep learning research, because in many applications that you create using deep learning, you will always see that when you have not large enough data, the data that are not varied enough, or the data that are generated from rules, many times your model will be overfitted, and that would make when you got overfitted models, it would not perform very well. So that's why we need to do the regularization. We need to have a way that you can that you can balance the trade-off between the objective that you have and the cost of using optimizing, of getting the right answers, right? Like you can spend a lot, you can have a lot of parameters working together, but if the number of parameters is too large, you can have overfitted model, and that will make the model unable to perform with the new data that is coming in, right? So that's what we are going to take a look at today. Right, so let's begin then. Right. So the topic will be about regularization, and particularly regularization for deep learning. We will take a look at a number of techniques that can be used to regularize or to make the neural network become less overfitted. And from today's lecture, after the today's lecture, you will see that by just having a slightly more variation in data, you can allow the model to learn better. That means if you want to do work in deep learning, one thing to consider is how to find the data that contain enough variations, right? If the data contain, if you see after you explore the data and you see that the data are not quite varied, using deep learning might not be a good idea. You would, I think, better off if you use something like normal machine learning that can cope with less variability in the data. But if you work with the unstructured data like a picture or a video that you see me right now, it can change a lot when you have when you have a different, let's say, viewing angle and others, and that would require techniques that can handle those types of variation, and that's what we are going to take a look at today. The technique that allow you to create variation in the data, that allow you to impose certain restriction onto the model, so that the model, when it learns, it has to also take into account on these criteria as well. This is not a new concept actually. It has been used in machine learning for quite a while, but this plays very important role to the use in deep learning. Okay, because of the main problem in deep learning is that the model, I want to have less pointer, right? The model need to learn from the training dataset, but it will also have to be good as well for the testing dataset. What does it mean? It means that after the models see or learn from the training data, it has to capture variations in that dataset and just capture the important variations, not every variations, okay? Just important generalizable variations, or sometimes we would call it insight from the data. If the model can do that, it should be able to apply the results, apply the model to perform with the new input. So there are many ideas, many strategies that can be used with machine learning that would reduce the test errors, like parameter tuning, like finding important variables, doing feature selection, feature enhancement. What we are going to take a look today is one of the fascinating technique that allow you to adjust the model by imposing criteria into the model itself, and that technique is called regularization. All right. Before we begin, I have posted the link. I have posted the supplementary reading for you guys. That one was the one that I worked on to show you how you can estimate the gradient of the each layer of the network. Because in the second assignments, you have to derive the mathematical formula again to derive the weight of the XOR learning, right? So I show you how to do it with the general case of the neural network inside the, I think it's called the supplementary lecture 6 something. You can take a look at that, try to read and understand. If you don't understand the mathematical derivation or any part or any equation, you can capture the picture, post, and ask me. Alright, I will try my best to explain to you on that sense, but try to read it first. Okay. You can find that in our Facebook group. Alright, for this time, for this lecture, let's move on about regularization. Right. One of the regularization that can be done and has been used in many of the machine learning techniques are what's so called the penalties of the, I would say, penalties of the weight of the network, or the penalty. The penalties of the network weight, or the penalties of the use of parameters. The more parameters that you use, the more error that it would contribute, the more loss that it would contribute. So one of the regularization technique that has been used, and we have seen that already, is something like ridge regression and lasso regression, by limiting the capacity of the model. Let's say if you limit the norm has to be small, you can incorporate such a criteria into the loss function, right, into the objective function, by incorporating this omega theta. This omega theta will be large if the parameters is large. Right? If there are so many parameters, then omega will be large. If there are fewer parameters, omega will be small. Okay, this can be done by controlling the norms of the parameters coefficient. Okay, so here alpha is the value is more than 0. This is like the value like lambda to tell the importance between the regularization and the actual error. So we have seen this in support vector machine. We have seen this in logistic regression. You have worked on that in the assignment number 1 a bit, right? So this is the penalty using the norm penalty. Let's look at different types of penalties. Suppose that we have the objective function in this form. This is J W, this is the weight, and for the inputs X and Y, we can write the loss function for this one equaling to the second part here. This is the original objective function, the original loss function, which can be the cross entropy for the logistic regression. It can be for the linear regression, the square error, right? So here, this one is the W and transpose and multiply or dot with W, right? As you can see that if you have the row matrix and you dot it or multiply it with the column row vector and column vector, right? You multiply them together, it's the dot product between two sequences. That would give you the results of a scalar value, right? It will give you scalar value as a result. This scalar value would indicate the loss that occurring when you have this value of weight, right? So this is the L2 norm, right, incorporated into the objective function. If we take the gradient, right, carried by W, then the W square, think about this as W square, right, the weight square. The weight square would be pulling 2 down to cancel with this out. You got only alpha W. and this is the gradient, the O gradient. What does it mean? It means that if you compare this one, the gradient here, to the original gradient, the difference would be that instead of having just the gradient alone, you have to also add the value of the weight itself. You have to add the value of the weight itself to an alpha here. Okay, so the update rule would be the original weight and alpha, the weight, and the gradient. Now if we rearrange things so that it would be something that is similar to gradient descent, this epsilon alpha, epsilon is the learning rate, epsilon alpha and W would be merged together, and it could be merged with W here. So you would have the new W equals 1 minus epsilon alpha and W, right? What does that mean? Right? This second part here is the same gradient. Right? This is the same gradient. But the earlier part here, instead of using the whole weight, you can see that instead of using the whole weight when you use 1, we now use less weight to update, to assign as the original value, right? By specific learning rate, we kind of scale it down, right? Scale the weight down according to alpha, right? Scale it down according to alpha, and then also according to the learning rate. Okay, this is how the new weight is updated in the L2 norm. Okay, what would happen here, right? You can see from this, you can see from the objective function that there are two contesting hypotheses, two contesting components in the objective function. The first component is this component, the component of the weight of the loss. If we just take the JW and then plot the graph, right, we would have the graph that look like this. You have this W. This is the lowest, right? This is the lowest error. And this lowest error would become larger, will become, when you kind of think about this as something like the contour graph, that is, this is the lowest point, and when you step up here, it will be higher and higher, right? So it means higher error. This is W1 and W2, so it's two parameter here. And the first term here, this is W squared. When you have W1 and W2, and then you plot them together, right? And then in the results here, you have W squared. You get something like X squared plus Y squared equal R squared, right? And that is actually a circle, right? If you remember your high school mathematics, right? The circle equation, X squared plus Y squared equal some number there. And we have here the second part here is the dot, which is actually the square of each dimension. So it would contribute to this this region. That is, if the weight is 0, then the constraint will be lowest. If the weight is higher, the norm of the weight is higher, you get a larger circle. The norm of the weight is higher, you get a larger circle, until it touched here, right? Until this circle touch with the line from the contour from the error function. When the line touch, that indicate that two constraints are satisfied. Right? That you kind of satisfy both constraints. This solution satisfies both constraints. That means W value here would satisfy the case that you have low value of weight according to this constraint, and also the low value of the as low as the maximum low value, I would say something like that. The greater it's not GCD and LCM, but similar concept, because you kind of satisfy the constraint together on both of them. Okay, and you can see that the point here, the point that touch between that indicate the touch point between the two parts here would be some point that are not on the axis. There will be some points, because this is circle, and this one is somewhat circular as well. When it touch, it will be some point here. That means we have low W for sure, the lowest W that it can have, and also the lowest error according to this one. Okay, so this is how the two constraints satisfy with one another, and why L2 give you low value but not equals to 0. This is called L2 regularization. Okay, for L1, this is L2. For L1, L1 regularization, usually we would use this as norm. L1 is actually the summation of weight. Right? If you use L1 inside the error function, it would look like this. So this would be objective function would be J of W, which is the same old J here, and this is the absolute summation, the Manhattan distance. And if we take a gradient, the gradient of this is the sine of W, right? It's the sine of W. Just take the sine, and the same one here. After, I think this derivation is a little bit hard here, and then you have to kind of adjust them so that it would fall into the same form. So that W, after you solve these equations, would get into something like you get the sine of W, and the maximum between the sine of W and the alpha over HII here. HII is the difference. This is the difference between weight and the approximation, because this is adding the sine into this. I think the better way to understand this is to just looking at the objective function here. Okay. In the objective function, there are two possible outcomes. The outcome that it touch on one axis. Look at this one. I think I have the picture here. No? Let me share another one. That would be better understood. L1 criteria. Regularization. Right, this one is should be unveiled. And let me open the picture. Okay, let me share this one. All right, so here, this is the ridge regression, which you can see that the touch points is some value of the weight. But if you use the L1, because the L1 would calculate the size of the vector according to just on each axis alone, right? The absolute size. That means the point that would be first touched with the criteria here, that you have like lowest errors and also lowest error in the first criteria and the lowest error in the second criteria, would be the point that are on the axis here, right? So that's the reason for the L1 approximation. If we take a look at the equation here, okay, you take a look at the equation here. You can see that from the usual, you have this as the size of W, right? And that makes the approximation of, if we approximate the J here with the quadratic approximation, that is the actual one, and the quadratic of the change of W, taking derivative of, because this one, if you take derivative of this one, it would be a little bit problematic, because we have this as a sign. There's no, this is just plus and minus 1. and the change in gradient. So in order to make it derivable, to make you able to adjust according to the gradient, you need to approximate the objective function here first using quadratic approximation, which in the quadratic approximation you take the value at w star and then add it with the change, right? The change of w square multiplied by this this value HII, okay, and plus with this alpha and then absolute W, absolute WI. This is the size according to the above here in the summation. So what is done here is to expand JW to contains not just the not to think of JW here, not just some value that change, but we kind of approximate it with the original value. So this is like when you have something like the S, the displacement, or the U plus U equal V equal U plus AT, right? That you have the velocity equal to the initial velocity plus the acceleration time t, right? So that is how you can approximate the function, approximate something like in physics, something like velocity with the initial velocity and the change in velocity. Right? That can be done here as well. That is, you can approximate function here with the initial condition at the point W star plus with the change in W and this HII here, which is the value of I would say the change once this W change at this point I, right? So we can from this one we can take derivative of this by curl it by WI and then solve to find analytic solution with down here. So that's how this can be obtained. Although in reality for the L1 and L2 we usually just specify the criteria, and you have done that already for the L2 in the logistic regression. Alright, so because here in this case WI would have two possible solutions depending on the value of the weight itself, the size of the weight, and the alpha over HII here. If the weight is less than alpha over HII, right? What does it mean, right? It means that the WI is under regularized, which is if this value is true, then it means that the WI would equal 0. Right? On the other hand, if the WI here is more than alpha over HII, then it would shift towards something that it equals to alpha over HII. Okay, so for this one, the weight of W has to be more than 0. Okay, so it would be a value that is very small. According to the L1 regularization, it would be the value that is between W equals 0 and the ratio between the alpha, which is the actually here, the weight here, and the change in the error. Okay, so it's kind of if the alpha is more than the change in the error and the weight obtained is more than this value, then it would not be optimum. You cannot find, it's like you find out that this is in infeasible region. But if it is in the above, then it would be regularized and the weight would be approaching 0, having low value. Okay, and some of and as you can see from the geometric that some of the value will be 0 because the criteria that satisfy for both conditions would be the case that they touch to one another. HII is something like the this is like the error that is from the J here, right? The change in the error according to the change in W. Right. So for that is the way that you that in machine learning model, the model has to take into account of the use of the parameters. When you take into account of the use of the parameters, right, the solution would be something like the optimum between the two criteria. Okay, whether it's L2, which the criteria would be some value here, or the L1, which the criteria has to be the value that have certain value. If it is regularized, it would have to be 0, because it would be the point that it touched one another. Okay. But there are other variations that you can choose as well, right? So those are something like the two classic lasso enriched regression that has been implemented in machine learning. Okay. So it looks like this one. You have the J theta. This is the original, and then you add it with the alpha or omega theta, right? That's how it is done. Now suppose that you want the constraint here to be less than some constant, right? In which case that you would want this? For example, you might want the parameters here to be low, but it must be lower than 1, not just low. Okay, it must be lower than 1. Like in, I think back to lectures, 2 or 3 lectures, when we talk about when you start doing the work in SGD, I think it's on the last lecture, I don't remember exactly, that there is the criteria in the MAP criteria that you want the value to be regularized and less than 1. I don't remember all the logistic regression or gradient optimization. And what you did is to incorporate into the criteria, linearize the criteria, so that you take the value here and minus 1, right? Why doing that? If you want the criteria here to be less than some constant k, right? Alpha minus k would do the trick. By what? If the value here of omega here is less than k, if it is less than k, right, smaller than k, then it means that the second term will be negative value. Right? The loss with negative value is actually good, right? So because it's like, well, loss means the more loss, the worse result that you get. So if you get a negative value, then that's good, but you often not in most cases, because you need to have a certain value to minimize the J theta here. So by putting it like this, right, you say that it would start from K that you would count as the error, as the loss would occur. Okay, so if you want the constraint omega here to say less than 1, you need to set omega here and then minus 1 in the loss function, and then that will make it the case here. And afterward, the solution is to optimize this constraint. That is, it has to maximize alpha, right? Minimize the loss theta and alpha. What you want would be to find the argument mean of theta. You want to find the value of theta that result in the lowest error, right? You want the parameters that results in the lowest error. Why? Maximizing maximizing alpha, right? You want the alpha here to be as large as possible, right? So that you would have the rules that could be generalized into different data set, right? You have the model that is less overfit. Okay, so if I were to speak in the human language, I would say that the thing that you want system to learn is something like you want system to learn the insight, right? The insight that is good, it should explain the data, minimize the loss. At the same time, it need to be simple simple but effective, right? So human language for this one would be, you want parameters that will make your model simple and effective. Okay, so yeah, that's the whole thing about norm penalty. Okay, so how would you approach that, right? If you have the constraint problem rather than the unconstrained one. Okay, in the usual logistic regression, as you can see, this is the unconstrained one. You can find parameters as according to what you want. But once you impose the constraint in, okay, you impose this penalty in, right? You have to take a derivative, and then you need to also take derivative of the terms here as well, right? How can you make that? How can you make that things a derivative there to include the constraint in the finding of the solutions? Let's look at simple examples in the case of linear regression. Okay, in the linear regression, we can identify the solution of the linear regression by performing pseudo inverse, right? Pseudo inverse is I should write it here. The pseudo inverse. It is the A transpose times A. Oops. The pseudo inverse is usually is A. Let's use X transpose times X and inverse, and then X transpose, and then you multiply this with Y. The one in square bracket here is the pseudo inverse, that you kind of creating a pseudo, right? A pseudo inverse that you can obtain parameters that when you have non-square matrix, estimate the parameters out. Now if you have constraints, what would happen, right? If you include the constraint to the equation, the result would be that you will have this term, right? Alpha I inside this as well. So that means the inverse here would have to include the diagonal value of alpha inside, right? And then with the limit of alpha approaching 0, you would have if the alpha approaching 0 here, that means the effect of this one would be negligent. But if it is quite large enough, then it would change the pseudo inverse value out. Okay, but you can see that we can approximate pseudo inverse by incorporating the constraint, and then it will be part of the pseudo inverse solution. Okay, so this is how it is done in terms of modifying the loss function, and then doing the when you modify the loss function like this, you may think, and what do you need to do? What do you need to do in order to perform regularization? You do the same. You just need to do the same thing like what you did in the first assignment. You take a derivative of this one and then use the gradient to update the solution. Okay, for linear regression, you can try deriving the equation itself, but you see that the constraint, when you incorporate something like the weight constraint to the linear regression, it would incur into some type of this form, right? As alpha. I think this is already in the lecture as well. And when you incorporate this into the model, and this would be added to the usual X transpose times X, which will contribute to something like the weight of the diagonal, which the diagonal in this case would mean when you have the value of parameters matching with the parameters itself. Okay, those are the way that you can modify the model, modify the learning algorithm. You can see that there aren't much choice. Mostly that would be constraint of the values to use, like the L2 and L1 parameters constraint that the value should not be large. Well, it worked to a certain extent, but in the case of deep learning, it is not always applicable, right? Because if you need to do this, incorporate this, it would mean you kind of imposing complication into the model. Which people did that, and actually there's the in logistic regression you have a constraint, but it does not really resolve the terms the root cause of the problem. That is, usually you would have the data that are not vary enough. That's the reason that the model overfit. For example, if you take the data from, if you create your own data set, let's say if I were to create a model that would, when I provide a question, and it would answer, I can create a question answer pair. Let's say I create 1,000 of them. But when I train the model would just capture this 1,000. If I have a test data set of another 10,000, it wouldn't work because you have the data that are quite limited. So how do we solve that? The case that the data, or say if you do if we were to create a deep learning model that recognize the image of dog and cat, and if that dog and cat image kind of translate a bit, let's say the dog image or the cat image is kind of rotated a bit because of the camera. How do you create a model that could take care of those situations, right? That means the input data need to be vary a lot more, and that is actually the idea of data augmentation. Okay, this has become the mainstream technique that allow you to regularize the network by creating a much harder version of the dataset. You may have your own initial dataset, but you need to create variations of dataset that contain harder examples, and then use those harder examples in order to put it into the model. Okay, so how to do that? You might already have something like this one, the true images. Then from the true images, you can deform them, transform them into another set. And then from this, you can use them to train the model. So rather than using just the dataset that you have, you can create additional dataset. Let's say something like super upsampling. Think about this as upsampling, but we are not really upsampling them. We are going to modify them as well. For example, for this image, we can rotate them around. We can deform them using a file transform to deform them. In the case of we see the image from the side or from the front or from the side up. By creating different perspective, we can transform them using a file transform. And then after that for each image we can synthesize the variations after we kind of creating a class specific distribution. We can sampling from them and then use these to train the model rather than just the image itself. So one obvious example is to use this image and then rotate them 360 degree, and you have 360 additional image, and then you can rotate them in this set as well, right? In the planar direction, and then do the projection. Right? What if you get this viewpoint, whether it will be this or it will be this side, you can rotate them around to get additional data. Like this one, dataset augmentation. From the images, you can transform the image by crop them, rotate them, put noise, and do whatever you want. You can merge them. Merge is not a good idea because you want label to be fixed, right? But you want to kind of make augmentation of the input data. Think about this as creating harder examples, like when you teach your child or when you teach your friend. You want to have harder examples so that the model would learn, but it would need to learn from the harder examples, and it would need to kind of become better in order to be able to capture the variation like this one, right? So this is very the thing that is that kind of strike me as you can see that researchers in deep learning try to use the method that actually we human use, but we try to teach them the machine learning to capture the pattern by seeing harder example here. Okay, so mathematically it can be explained like this. This is for noise injection. You have y and x and y in pair, and then you have this one, the error or the noise, the white noise. This has distribution, say the normal distribution, mean zero, and certain variation in the covariance in x and y, and the objective function of the optimization now would change from comparing the actual y, from comparing between the y and this prediction of x, right? Prediction of x and with some variation here. The error would be the error not just between the two. It would be the errors of this would be y square, and this would be y square with the errors, and then multiplication with of y, and then the error of the y with the added noise. So here we would have the new objective function that not just minimizing the true class, but also minimizing the true class prediction with noise, and that would make the model able to adapt to the noise, to the change in the input. Okay, so in the picture, noise injection would be something like this. You have the forward propagation going up, then you can add noise, and in the error part here, and then doing back propagation. So what would happen here by adding noise? So this is something that is not, it is different. This is, for this one, you kind of adjust input. But for this one, you kind of inject noise into the prediction. Inject noise into the prediction. Say, suppose you predict something, then it will be randomly adjusted. Just like that. Right? The output will be randomly adjusted to certain noise. That is something like decision noise. So the decision noise will be vary according to, so this is like the decision noise alone, the error will come decision noise alone, and the interaction between the actual value, whether this is like high value, low value, together, or change according to, or in the opposite side. So it works like this one, for propagation, adding noise. Then from this noise added, you can see that the error at the end would be propagated back to the back propagation. That means there could be some errors, right? From the large gradient, it can be larger gradient based on noise, but the input are the same. That means the model has now to adapt to these variations. You need to adapt to this variation, even though you have the fixed input. We have fixed input, but by doing forward propagation and backward propagation like this one, you kind of creating variations, a chance for the model to learn. Think about it this way: if you have fixed example and fixed output, the model would just remember that pattern. But with this one, right, the model would remember the patterns that are important. Those that are not important would be disrupted by noise. By adding noise here, those that are not important will be disrupted. So this is one of the great idea to do that. In your term paper, right, try to take a look at the method that you pick, and you will see that lots of technique in deep learning try to aim to handle these types of regularization. Right, many of them will be about data set generation. Some of them would modify the learning to add something like noise, or like additional image, or the adversarial example into the learning process. Okay. You can create a system that, in order to avoid overfitting, right, we can do the semi-supervised learning, because many times, the reason that the model overfitted is because you have limited data size. How to do, if you have limited data set, how can you train the model so that it works very effective, it is effective to a larger data set? One of the approach is to perform semi-supervised learning. In a semi-supervised learning, you need to build the model first with labeled data that you have. And then you can place the unlabeled data into the model. Use the model to classify the results and build another one. Right? So the classifier would kind of achieve better generalization along the way, right? By predicting and then grouping and then trying to learn new patterns. Okay, this is semi-supervised learning. A very good idea to work with when you have limited labeled data but large size of unlabeled data. The one that does not belong to each of the class should be ignored. That means those are patterns that are quite hard to learn. You can just disregard them first and then use the one that you are sure to belong to this class to train the model again. That would improve the dataset scenario. Okay, this is one of the cool things that I like about deep learning is that you can train the model once, but aim to make it to perform multiple tasks, doing the multitask learning. Think about deep learning as the feature extractor. That is, you can use the deep learning to extract parameters and to extract different patterns from the data. And then you use those extracted features to perform classification, for example. Right? So you can have these layers. Say you can have this neural network layer shared between multiple tasks. Right? By having the output of this one fetch to the network head here, the other output, the same output actually fetch into another network, and this output also fetch to another network. And in the end, you kind of use these two to give you the errors, right? To calculate the loss from just these two, right? So you can have the two layers separated. The lower one can be the shared parameters. This parameter has to be shared because you kind of have task-specific parameters above here. So the models would learn in a way that H1 here would be specific to to the task 1. H2 would be specific to the task 2. But H-share will be specific to a general class. What types of data should we use in this case? For example, if I have X here as the stock data, and I want this stock data to predict future profit, at the same time assess future risk, right? You can see that these two are the different things, aim for different things. One is to predict say where the rise and fall of the stock. The other is to predict the variation, right? The risk situation of the stock. Then, but there should be some shared features like pattern extractor, seasonal data extractions, trend estimations. Those are the things that should be learned together here in the H-share. So by configuring the model so that it divides the output into two heads here, and it has like multiple output, you can improve generalization of the model. It has been proven it has been reported in Baxter in 1995 that by shared parameters, you make the model better. And actually, an obvious example is the CNN. When you have a technique like CNN that share the parameters together, when you learn in a different way, you can handle unstructured data. Right? So that means by performing multitask, or sometimes it's called multi-head because you have multiple heads here, multitask learning, you let the system learn parameters, learn data in hierarchical manner. Okay, so this is multitask learning. Okay, another technique that is often used, but it's very simple idea in deep learning is called early stopping. When you train a model, you need to decide how many iterations, how many epochs you want to use. Early stopping means that, well, let's say if you hit the lowest value 2 times, if you hit the lowest value and then go up 1 time, 2 times, then you should stop at that point. That's called early stopping. This can be incorporated into the callback in the callback API when you train the in Keras. So what does it mean? It means that when you kind of reach the point that it is lowest, validation test set loss is lowest, and then it kind of increase, it will stop at that point, because the more you train, the more overfitted the model will become. That means you need to kind of stop at, from this one, it may be at 7 iteration, 7 epoch, for example, and then you should just stop there, or else your loss will increase. Okay, this is called early stopping. Don't know why we have to make it into algorithm, but the idea is very simple here. So let's say you have train set X and Y, split train set into subtrain, validation, right? Train and validation, and run the train and validation, right? Run the train and validation to see what is the optimal number of steps. Once you know that, just train the model again. That's it. Right? So train the model, say 20 iterations, and see, okay, maybe at the 5th iteration is enough. Retrain the model again at the 5th iteration, right? With the 5th iterations, 5 epochs. Right. So that's the way to do that. This is another variation. It's called parameter tying. This is also a way to address the problem. You've encountered this parameter tying. Well, I should mention, right? Multitask learning, you see it later on for sure when you, well, this is like the choice that you want to make when you have a task in the multiple layers. But a task like this one, multi-parameter tying, the idea is that you have similar tasks doing with A. You use function f and w with A, doing with B. In the other part, you have the G with B. And you kind of saying that the difference between W should be small, add non-penalty to that. What types of network requiring something like this, parameter tying? When we train a model using, when we train the text data and then perform embedding, right? Trying to learn embedding. Embedding is actually a type of parameter tying, because you're creating a lookup table that is used for any word that comes in. It has to look up at this table. So the parameter need to be tied. The parameters of the network, of the table, will be tied together. You kind of need to learn once. Or in the Siamese neural network. In the Siamese neural net, looks like this one. In the Siamese neural net, you kind of having two networks that have the same weight, and you give it with two input and try to compare the output so that the output would be small if they are the same, should be large if they are different. You can use this type of network to compare image, to compare text, to compare video, compare frame, and many others. If you want a question and answer, to do the comparison like that. But the idea is that the weight need to be tied. The weight between two have to be the same. You're kind of creating the same thing, the comparison network that will compare two input together. Okay, this is called Siamese neural network. You can see that the parameters are tied. So this is the concept of the parameter tying, that you tie the parameters together, even though they are learning, they are from two paths, but you kind of saying that they are the same. This parameter tying would reduce the specificity of the network, and it would make the network become less overfitted, right? When you when learning, the learner try to compare the analogy between different techniques, right? As I said, this parameter tying, you will see it again later when you learn about embedding. But many people do not realize that they are actually from the same concept, right? And when you read the paper, the research paper, you will see that, again, you will see parameter tying, right? They use the same weight. Why is that? Because when they use the same weight, they try to learn just one weight that perform one task. I'm trying to say that it's really one task. Like in the Siamese neural net, the task is to just extract features. So extracting features should not be different when you have two networks. That's why they decided to have something like the same weight for both networks there. This as well. Okay, parameter tying and parameter sharing, right? This should be explained at best when you learn about convolutional neural net. The convolutional neural net share parameters when you analyze the pattern of the whole network. That means of the whole picture. When you have the whole picture, you're trying to create a set of parameters. Right? Say I would draw this picture. You try to create this 9 by 9 grid, 3 by 3 grid. This 3 by 3 grid will be used to apply from the top left and then going down all the way to the end to create the next feature mapping, right? To create a convolute image feature mapping, a set of them, one set for one mask for one set. You have a multiple mask. It will be learned for multiple set of them, right? But you can see that there is the sharing of parameters, because unlike dense layer, when we work with the dense layer, when we work with fully connected network, right? In the previous lectures, in the fully connected network, when you analyze the picture here, it kind of using all the point, and then from all the point it should fetch to just one node. Okay, so if I were to write the dense architecture, it would be something like this. Say we have 4 by 4, and we have say 3 node, and so on. Here, for one node, it kind of need to be connected to all of the input. This is for the dense connection. Dense connection. So there are so many parameters for each node here, and the second one as well. So many parameters. Unlike the convolutional neural net, that is, you have just 9 parameters shared and used throughout the text here. Right? This is called parameter sharing. Okay? You will see that work again later when you learn about convolutional neural network. Okay? It reduced the memory footprint. And it also allow the model to generalize, to learn just a small set of value that could distinguish between the model. So it doesn't mean that when the model is complicated, it's good, right? Sometimes less complicated model is better, because the model has less chance to be overfitted. So here, when you do convolutional neural net, you kind of convolute them 3 by 3, creating a feature map, and this convolution will be shared together throughout the image. Okay. Well, there are many things that can be done, right? To perform regularization, you have seen the norm penalties regularization. Let me recap it again. Using norm create penalties, creating the augmented data set, inject the noise into learning, doing the semi-supervised learn more patterns, creating the multitask so that the network need to learn to perform multiple tasks at the same time. Right? You get the share feature out. Do the early stopping, reduce the time to learn, tie the parameters, tie the same task together, right? Creating the sharing of parameters when you want it to just learn one pattern. Right, and you can see that all of these techniques try to create harder situations for the network to learn, right? And I hope that you will find these type of things in the paper, that when you review the paper, and it's quite funny to see that They're just creating something like hard example, and the network need to cope with that, and it can, right? And it kind of allow the system to well overcome that difficulties and learn the kind of generalized pattern without having to learn something that are unnecessary. Okay, right? So it's like when you watch YouTube. Let's say you watch YouTube, you watch lots of YouTube on the same topic. You kind of learn the concepts, overall concepts. But when you just watch one and then remember just one, that means you kind of overfitted to just one lectures. There might be other concepts offered elsewhere as well that are useful and has not been discussed. So yeah, that's it, the type of analogy there. Right? Okay. So let me check. Okay, it's quite short, but anyway. So what else that can be done for regularizing the network, right? We want to do that. One way to do, again, is to make life harder for the model, right? Put in the life. The model now would have lifetime. If it doesn't adapt fast enough, it would die. Something like that. Right? So put the weight decay, right? In weight decay in the penalty. Weight decay by placing penalty directly to the model parameters. That means the longer you adapt the parameters, the value would be decay. The value would be decay towards zero. It would be reduced all the time towards zero. Weight decay would encourage the activation of the kind of a sparse representation. That is, if from the layer, some of the line does not really have to be used. Right? If in the dense connection, some of the line does not really have to be used. Let's say this line does not really have to be used. By putting weight decay there, the weight would kind of become approaching zero the more you train the model. If it doesn't have to be improved. If it is not important, right? So the weight would be decay down. So this is a strategy that would kind of encouraging the network to activate the part that are necessary, okay, and create something like this sparse representation. This concept is the foundation of attention. Okay, there is a method called attention, which kind of imposing they try to learn that which part of the image should be focused on, right? So, and to create sparse representation like that. So many of these techniques relate to current development in deep learning in many ways. And yeah, many of you may have already seen this. This is a way that random forest work. If you want to make the model better, is to perform model averaging. Model averaging can be done through the ensemble technique. One of the ways to do ensemble is to sample the data into multiple sets and learn it, creating multiple classifiers, and then combine the result later. Right? This is the backing of the model. Although this will be a little bit difficult for the deep learning, because you may have seen that in deep learning, in order to create backing with like bootstrap sampling, this would be a little bit hard, right? To create bootstrap sampling, train multiple model. But believe it or not, that's actually a technique that uses backing without us realizing it. Can anyone tell me to check whether you are still awake or not? Which deep learning architecture? Well, some of you may have not seen, but some of you have already taken the coding in that course and others. Which deep learning architecture relying on something like bootstrap aggregation. Which one? Which one create multiple output of the same things and then aggregate them, average them together, or combine them together? Which technique? Let's see. Okay. Random forest. Yes, random forest. I mean for deep learning. Well, random forest is for sure, right? But for deep learning. And anyway, I actually have already put in that. Yeah, random forest is right. I mean this one. This one rely also use similar concept to comparing to deep learning. Why is that? Because you can see that for each of the convolution, you create a feature map. For one mass, you create a feature map of the mass. One mass to create a feature map of the mass. Each of the feature map of the mass here represent a pattern that it has detected. Then you can combine feature map together. You can combine the feature map together to get the lower dimension. This is called pooling. You can combine it in spatial domain. You can combine it in the feature map layers. You can combine it if you work with the time data in temporal layers. Right? So this allows you to summarize, right? Sampling, it's not sampling per se, but it's like having multiple way to copy the data and then summarize them. Right? So work in similar way here. Right? This is the bootstrap aggregation. Bootstrap aggregation would reduce the model errors. Right? The reasons that when you do the K regression model and it reduces the errors is because if you take a look at the expected value of the error square, this expected value of the error square comes from you have the error of example I. This is this would be the summation of the error of example I plus the mismatch in the case that j not equal to I. This is if it's equal to one another. If it's not equal to one another, when you perform expectation of this one, you get the results as this 1 over k of v and k minus 1 over k of the certain constant value. And this means that the variation in the data would be reduced according to the factor of k. The rationale of the regression, having multiple regression model, is that you cannot reduce the variation, the variance in the data, right, according to a certain factor of the model provide, or I would say the number of the tree that you have, number of the model that you have. This is backing. Although backing is difficult to implement it in deep learning because you have to create multiple deep learning model for performing the same task, and that is quite computationally extensive. But as I said, maybe you can think of the algorithm that doing something like bootstrap on the data. You can see that CNN doesn't quite reach that point yet because CNN contains no randomness. Well, it contains randomness in the mass, but it contains no randomness in the spatial data. So it means if you maybe research in this field, you might invent some cool things by incorporating the concept you have seen in machine learning to the deep learning one. And maybe what I think right now has already been published. Many times I find that, oh, this is a good idea. Maybe you can combine those and those together. And then I searched the paper and I found, oh, someone has already done that. Many times like that. Now let's come to the popular one that in the deep learning, although it's quite routine, it's very simple to implement. This is called dropout. Dropout train it's kind of dropout would when you train the model with dropout, it means that you try to remove some of the output out, some of the unit out. For example, for this one, these are the possible combination when you perform dropout. Like for this fully connected network, you can drop x one thing, you can drop s1 out, you can drop x2 out, you can drop h1 out, you can drop h2 out, you can drop both input out, which I don't know why you want to do that. You can, but you can see that there are multiple nodes that can be dropped, especially inside. Why do you want to drop the node out? Because sometimes by pruning the tree, by pruning the node, it allows the system to grow, right? When you prune the old knowledge out, you can learn more that way. Do you know that actually in human brain, since our birth, right, our brain will try to prune the thing that you haven't done out. That means if you want to be good with English, you need to practice English, right? Talk in English. Otherwise, your brain will prune them out. Okay. If you want to be good at game, well, try that. If you play games, you are very good at certain games, one time, but you kind of got bored, change games. Your brain will prune that out. The skill that you learn in that one will be gone, right? And then when you come back to play again, you don't know what to do, right? That's not the old age, but that's the pruning of the brain, right? So dropout works like that, right? It would kind of prune the tree. Although mostly it would randomly prune the tree. Maybe if you find the research in dropout, this would be great, right? Let's see if there are certain preferential dropout. I bet that would be, for sure. So in the no dropout means that you have fully connected one like this one. With dropout, you can have the network drop at some of the node out. By going for each of the node and say that you have certain parameter, say 0.5. 0.5 here would means that you have a certain chance to drop each of these node out. And once it's dropped, then if it is dropped, then you can use just the average or whatever values to use here. In implementation, it's very simple. You can just put the spatial dropout or the node dropout into as one layers in the network. Now let's look at this one. This one is very interesting example, and actually it has become quite a trend 2 years back that they even create a t-shirt. If you don't want your government to spy on you, not in Thailand though, I don't think we are at that capability to scan yet, given that, let's say, if the CCTV can work, that is already amazing. I don't think we are at that point. Well, say in China, in US, if you don't want government to spy on you, there is a t-shirt that you can buy that it will kind of having this noise pattern, or certain picture with a noise pattern. Then the system will not recognize you as a person. That means if you cross the road and there is the self-driving car coming at you, it will just crash onto you because you have this the noise layer that will kind of confuse with the system. Right. So this is called this is called an adversarial example. Right? Adversarial example is created because the researcher find out that when you train the model like this one, and you get the model that can classify, say, panda with the around 60% confidence, and then you take the gradient. In the case of nematode with low confidence out, and then add this as error onto this panda. This would confuse the model because you kind of update the weight. You kind of hack the model. Update the weight by adding this in, you update the weight, but you update the weight toward another class, toward nematode. And this would make the life of the system difficult because once you train the model with certain with this using adversarial sample, it would kind of falsely classify the sample into another class. Right? So this is a way that you can attack the example by making the example containing the gradient of another image of another class. Why doing that? So that you can create example that is harder. By having something like this, you have the latent space of the image. Then from this latent space, you can generate the noise. Right? Latent space is something like you have the gradient of the image of the class, and then you use that gradient of the class to deciding whether this would be real or fake example, and then let the system learn the discriminator which would need to classify whether this is real or fake, and use the classify here. If it can detect, then use the error here to tune the network here that would generate the fake examples, so that the network generator here would generate the example that is close to the real one. Hard to recognize. Okay, why doing that? This is another slide that I just add in, so that you can create a training process that is harder. Okay, how to create classification model with adversarial examples to perform image recognition that is harder. Let's say we have this. We want to perform classification of the emotion. Right? We have like target data set, and we have the emotion data set that you want to incorporate it in. We can use this both to say compare whether they are in the same same class or not through this image, fetch to this image, and then you can see that the source data set would fall into classification of the class. This is what we want to do, and then the target data set that we want to use would be fetched into this adversarial module. And adversarial modules would contain the image from the source class to use it as to use the source label and the noise C and the noise C here as well, to train the adversarial to classify whether this is real or fake, with the class here as well. And when you have the data coming in, you can use it to perform classification using just the above part, right? That is learned through this, right? To perform classification of the class. So that means the type of adversarial examples will be used in the learning process. At the same time that you kind of adjusting the system to be able to generate learn distribution of data. You can find other examples as well, because this is just image. If you want to perform adversarial with the text, it's a bit difficult because noise in the text is not easy to do. Text is more like discrete value, right? So image is easier to understand. Okay, you can pick this one as well as the topic that if you want to present it to the class more about this, because I just going quickly going through this one. Okay, and there are many other strategy. Cannot cover them all, and each of the slides that I put here, they are one papers already. So it is impossible for me to cover everything up, but cover all the topics here. But what I want to show you today is that this is still a hot research, an active research that that many of the people in the fields, they are still trying to find the best way to regularize the deep learning. The goal is to reduce complexity, make the model simple but effective. Right? Remember this one. You want the simple model but effective. Okay. So for this one, I would encourage you to find more papers in this and discuss, especially about this, the regularization in the terms paperwork. But if you find that in the paper you want to present about architecture, that's fine as well. There are many interesting architecture like transformer, like sequence to sequence model, and many of the configuration that are quite interesting. But regularization is also one of them. Okay. That is actually all for today, right? That. So today's lecture cover most of the idea on on the regularization. I want you to see that there are multiple ways to perform regularizations, and each of those actually trying to create a more difficulty situations for the model to learn. At the same time, enhance the learning capability so that the model could capture the data. And the balance between the two would be the solution, would be the ideal solution of the learning process. Okay, so just like human, right? We want a lot of variations to learn the concepts. Once you have multiple sources, your brain can find out consistent pattern, generalizable rules that you can use. Right? Any questions? Please ask